Number 2 and number 8, we're okay? So whoever said yesterday what was number 1, maybe it wasn't that bad. Okay, number 14, you guys need to define the components. You need to define the components and the magnitude. Are we okay with the terminal subtracting the initial to get the component for horizontal and vertical? That's okay. And then, are you guys writing vector arrows because you're not just copying it out and they put a bold letter so you put a letter? Are you actually being like, no, it's a vector and I know what a vector is and I know what arrow comes from? Check your notation. Oh, what's going on here? Oh, it should be easy. I'm just testing that you know what the double lines mean. What do the double lines mean? You're finding magnitude and you're plugging into a squared plus b squared square rooted and then you're simplifying. I'm just checking. I'm just checking we know what this means, right? There's a lot that's written in your notebook that I'm pretty sure you might not know what it means. And we subtract and then we solve and then simplifying radicals. Are we okay simplifying radicals? Should be. If not, remember he's a 4, he's a 5, and what's the square root of 4? 2. What's the square root of 5? I don't know. Perfect. This ends up being 64 and 2, 128, I guess, right? So square root of 64 and square root of 2. Got him. All right, keep going. Ooh. What's going on here? They give you a vector v and all of a sudden you're finding a u and there's a division? I'm being facetious. I know exactly what's going on here. What were you finding in this one? A unit vector. How do I know it's a unit vector? Because they're starting with a vector and they're scaling him back by the, who's this guy? The magnitude. Yeah, the a squared plus b squared. Square root. So I can take any vector and I can scale it back. And why am I scaling it back? I'm saying you had a magnitude of what? 13? You had a magnitude of 13 in a unit vector. I need you now to have a magnitude of 1. Now think about it. You had a magnitude of 13. I need you to have a magnitude of 1. So we multiply the whole vector by the 1 over. Or we divide the whole vector by. Why am I talking about this for so long when I literally wrote it as a formula in your notes of what you do for a unit vector? Maybe you didn't understand, so you have no clue what to do on number 60. What was the weird magnitude of 10? We're going to pop ahead to 63 right now, even though I know it's not next and I know it's not an unit. But number 63. Number 63, it said, here's a vector. Make him a magnitude of 10. And you're like, well, I just did a magnitude of 1 a second ago. That should have been like unit vector. Making a vector with a magnitude that I want. Wait, that's not the one I want. 49? Aha! Thank you. Unit vectors. They're not yelling, they're just being cute. Okay. Unit vector says, I want you to have a magnitude of 1. We just had like a special term, unit vector, and I wrote a special formula. This one says, I want it to have a magnitude of 10. Okay, fine. But just like we did with unit vector, what is its magnitude now? Same thing we did with unit vector. We asked, what is its magnitude now? And in this one, what was its magnitude now? 13. He had a magnitude of 13. I needed him to have a magnitude of 1, so I divided everything by that 13. Check out this one. I needed to have a magnitude of 10, but what does he have now? How am I going to figure that out? Look. Why is it 5? Yeah, maybe you know it's a 3, 4, 5, but if you don't understand how this is really just Pythagorean theorem, you would have just plugged into your formula and said, whatever, I'm a good physics student, and if there's a formula, I'll plug in. So, plug in. 9 and 16 is 25, square root of 25 is 5. Just like unit vectors. He had a magnitude of 13, I needed him to be 1, so I divided everything by 13. This one. He has a magnitude of 5. I need it to be 10. What do we do? Double it. I just need it to be double. The other one, I needed it to be scaled back and everything divided by 13. I needed to get that 13 down to a 1, but this one, I just need it to be doubled. What do you need to be doubled? The whole triangle. What if I double the whole triangle? What are the new vector components going to be? Oh, yeah. As easy as that. But is this like the one problem out of homework that you couldn't have necessarily gone straight to a formula, straight to a concept, straight to a vocabulary? Yeah, it was weird when you think about it. But check it, guys. If they ever ask you either for a unit vector or for some weird magnitude, just figure out what you got first. Figure out his magnitude first, and then are you scaling back? Are you dividing by that? Or are you doubling, tripling, quadrupling? I don't know. Do what you got to do. Okay, so doubling it, good, that was perfect. And then the rest you gave me the right answer. Perfect. -6 and 8. I know it was an odd, but it was probably, I think, the most out there question in homework as far as not tying to our notes directly. And in math, man, give me stuff that's a little bit weird, a little bit out there. I'll go have someone else do it for me. It's really easy and really tempting just to give up a lot quicker than you would otherwise. Even though that's the time to dig in and actually try to use these skills that you've been building and say, can I figure out a weird problem on my own? Number 54, I think it was like a terminal minus initial thing first, right? You get your components and then linear combination. You guys okay with they really mean the same thing? This is called components, the side brackets. This new notation is called, what's this one called? Linear combination. And I is a vector and J is a vector. Check your notation. Are you putting those arrows above? I know they're bold. You're not writing them bold. And after that, 72. See that magnitude cosine angle, magnitude sine angle that I had you guys quote like 4 times yesterday? You could have just plugged and chugged. But for some of you, to be honest, you could have drawn the picture and been like, of course the x component is 0. It's straight up. And the y component must be the whole magnitude. If you were one of those problem solver types. Maybe the visual would have been a lot easier than the plugging in. But still, magnitude cosine angle, magnitude sine angle. Good physics students. Go to the formula and plug it in. Hopefully have some understanding of what's going on. Now, what happens after number 70? Ooh, that was an odd, right? 75 or something? Okay. Just because I was like, oh, I think there might be more to it than that. Okay. For number 75-ish, you were still trying to find the component form. You were still given magnitudes and directions, except you were supposed to be finding the sum. So this would have been like the picture I had on the board yesterday with, okay, we could do the geometry, or we could just say magnitude cosine angle, magnitude sine angle, magnitude cosine angle, magnitude sine angle. Add the x's, add the y's, I'm done. But all of this was getting us closer and closer and closer and closer to the actual application. Okay? So I want to go tackle the actual application. I want to get back to that weird system of equations problem that we had yesterday, where, to be honest, the math at this point is going to be trickier than even the picture. It's basically algebra 2. It's basically solving a system of equations, but the math is going to get tricky. But before we do that, how many problems are literally left in your homework to do for if you stop at 75? If you went through 75, like the directions said. I think I just gave you 3 word problems, right? Did I give you 4? Okay, so where are the 4? You have something in the 80s. You have something in the 90s. Oh, I gave you an odd and even. Okay. You have 4 word problems, and we have 3 examples. And some of you might be like, those word problems are disgusting. They're long. They're awful. They're... He looks kind of short. Except, Aiden, I'm coming to you. Except, some of them, the math is easy and the concept is hard. And some of them, the concept is easy and the math is hard. And I guess, theoretically, sometimes they're both hard. I'm going to get to the word problems, but I am curious, is there anything up to this point that we have homework questions on? I'm going to take Aiden's first question. I don't know what it's about. Yeah.
I just need help understanding number 35.
35, okay. No, that's totally fine. Kayla. 85. Is 85 that first word problem? Oh, don't worry. We're going over word problems today, and that's why you were supposed to stop at 75. So hang in there. But if I run out of time today with examples, we'll be doing word problem questions tomorrow. Got it. Sid. 75? Well, for today's submission was sans word problems, aka without, aka you were just supposed to finish up through 75. So as far as Google Classroom, not at all, because you weren't supposed to do them yet or didn't have to do them yet. As far as for our spot check tomorrow, it would be a 0. Spot check meaning not Google Classroom submission, meaning don't all go and unsubmit your homework and then resubmit with the word problems. Just have your work for the 4 ready to go tomorrow so I can do a quick, like, hey, did you try them all? As you guys are grading them, and then we'll go over questions. And then technically, if you still didn't do them, you had the 0 tomorrow, and then in the homework spiral, you probably missed like a half point out of the 3 points on your homework for not finishing your homework. Okay. 35. And then 75. 35, okay. You guys tell me, why does 35 look harder than it really is? Yeah, exactly. No, that's perfect. It has I's and J's. It looks harder than it really is. We did yesterday in our notes, we did like adding vectors, subtracting vectors, maybe 2 days ago. We did this in our notes, but only when we were given components, not the weird I's and J's. So the I's and J's make everything look a little bit harder, which is why I was kind of advising to take the I and J notation and think about it in terms of components if you're like, I don't know what it's saying. But if you realize that, and this one's probably the easier one to do that with, the V vector. I see a 2, I see a -3, I can just ignore the I and J. This one's a little bit harder until you realize, oh, duh, the understood coefficient of any variable is 1. Once we get the components, Aiden, I think everything becomes a bit clearer. As long as you remember that to add vectors, we just add the horizontals and the verticals. We just add the horizontals and the verticals. So then, like for letter A, all we have to do is, and I won't go through all of them, but we just have to do 1 + 2 is 3, 1 - 3 is -2. But they're not going to write that as their final answer because it wasn't in components. So then you guys help us out and throw it into linear combination form. What would it look like? 3i minus 2j. So that's what they're looking for, like for letter A. Does that make sense? So yeah, it's the i's and j's. It's just throwing you off. Is that cool? So then for B, just subtract, and then for C, just double the U to be 2, 2, triple the V to be 6, -9, then. Yeah. Okay, and then number 75 said that was that vector sum, right? The component form. This one I said quick, but there are a lot of concepts that are behind the quick that I said. So real quick, I just said quick like 10 times. That's annoying, sorry. I should be quickly. Let me review a couple things real fast. In that I see components and I see sum, and maybe I remember from yesterday, it's a lot easier to add vectors, including in word problems, if I have their components. Because I can just add down the horizontal, add down the vertical. The problem is I don't have the components yet. I have the Despicable Me version, I have the picture, the geometry version. So instead, what I'm going to do is I'm just going to be a good physics student. And remember, if I ever want the components of any sort of vector, I'm going to call it W just because these are U's and V's. Remember, all we have to do is magnitude, cosine, and magnitude, sine. Ultimately, it's taking us to a right triangle, and it's plugging in what we know and solving. Some of you are like, it's way easier if you just draw the picture. I know, sometimes it is, but sometimes it's not. So for those of you that are visual, you drew the picture, yeah, I get it. It could have been faster. But for the rest of us, we could have just plugged it in the formula. And since I can tell you right now, you're going to be able to make a formula card on the Chapter 6 test for anything from Section 6.3, 6.4, 6.5. Including all of these formulas, all of these diagrams, all of these word problem examples. You even do like a half sheet of paper. It doesn't even have to be a card. Honors had to fit it on a card and had to leave out a lot of stuff. But you guys, if you're going to be able to make a formula page for yourself from anything 6'3", 6'4", 6'5", there are great formulas to plug into. So at this point, Sid, I would just say, you know what? You have a magnitude. You have an angle. If you know that cosine of 0, can I make that jump? Unit circle. Cosine of 0 is 1. Sine of 0 is 0. I can do 5 times that cosine and 5 times that sine to get his component. Is that okay? I'm plugging in. So I'm doing 5 cosine 0 and 5 sine 0. And for V, now I'm going to 90 degrees, still magnitude of 5. Cosine of 90 is now 0. Sine of 90 for the vertical is now 1. So I have 5 plus 0 is 5, and I have 0 plus 5 is 5. Yeah. This one just said find a component form so we can be done. Other problems might be like, okay, that's great. I'm glad you like components, but no. I care about, they might, like in word problems we'll see, they might ask for the magnitude or they might ask for the direction. Then I would have to keep going to get out of component form. But yeah, this one says stop. So don't worry about it. Okay. You guys heard me say just a second ago that you can make a formula page on vectors and anything after, right? Okay. To that end, can we really tune in to making good notes for ourselves on the word problems I'm about to go over? Yeah? Now, this stuff, he can't go on your formula page. Law of sines, law of cosines, I'm like, no, there are a few things you still need to memorize. But starting at vectors. Oh, you're showing me this. Work on that. Okay. When you do, post it in the comment. Okay. No, this is an old one. Hold on. Wait. We weren't even in vectors yet. Although we could have been in vectors for this problem. They just snuck it in before we covered vectors. We're down here with the 2 cranes working on the load for the crate. That's really, really heavy, right? Yeah. There we go. Okay. This is one. You might not like what I'm about to say this, but I need to. This is one where the concept is fairly easy, but the math to actually solving is hard. This is one where the concept is fairly easy. The math is pretty hard. Why do I say the concept is fairly easy? What did I use to set up the components? Yeah, the equation. The equation with magnitude, cosine angle, magnitude, sine angle. Now, I didn't have the magnitude, so I know I put an x and I put a y, but we're used to that in math. We don't know something. We make it a variable. No big deal. But I was able to use my formula to say, okay, I don't know you, but I know the formula. I don't know you, but I know the formula. Got it. The weird negative positive thing, because it's the second quadrant, and it really gave me the first quadrant angle. Okay, that's a little awkward. A little conceptually difficult, but okay. Maybe you guys can, hopefully you guys yesterday saw that this one was pointed a different direction than that one. So I have to say, you're working horizontally the other way from you. And I, once again, didn't know his tension, didn't know that magnitude, but I did know the angle or the formula and the angle, so I was able to plug that in. And then once I have components, the concept is pretty easy. U plus U need to be that, and U plus U need to be that. Now this one was a little difficult, a little bit, because they were working together to lift up. I actually drew the picture to show the resultant, to give myself a better idea about how it's not horizontally. They're not horizontally moving this crate at all. They're strictly vertically moving it up. So horizontal displacement is 0. Vertical displacement is, or vertical magnitude, maybe I should say, vertical component is going to be that weight that it has to offset and it has to lift. But the setup was like, okay, U combined to be 0, U combined to be 20,240. The setup wasn't too conceptually difficult based on, okay, it's a sum of 2 vectors. I want components, and then I just put it together and say, all right, now what? The math is just going to get a little bit messy for some of you. Now, what is our goal again in working with the calculator? What's the word that I've been using over and over again, how I'm trying to make you more and more people are probably having good ideas. It's just not the exact word I keep using. More and more efficient with our calculator, efficient with our time, efficient with our resources, efficient with our tools. If you're in some sort of science or math lab, there are like these 3-hour labs in college that are kind of a mess, especially if you're going the medical route. You're going to be doing a lot of number crunching, and also a lot of maybe like forming charts and tables and all sorts of different things and writing out your lab summaries and your procedures and all that jazz. And yes, you'll have a lab group to work with, but let's be honest, they're not always that great. If you're doing number crunching, I want you to be able to use this efficiently if you're allowed to use it, right? Laura, what was your question? Just can you wait until after we go through this word problem? Yeah. Just if you don't see the word problem examples, it's nice. Okay. We need to solve for x, we need to solve for y, and the math is pretty basic in that it's a system of equations. Yeah? In systems of equations. If I could make this coefficient match that, couldn't I just add down he gets gone and then I just solve for y? Right? No enthusiasm whatsoever. If I had something like 3x minus 2y equals 10, and I had something like, I don't know, let's say 5x plus 4y equals 3. Algebra. You guys know what I'm talking about, right? X's and y's, two equations solved. If I could make these two match, double that whole thing, add down, solve for x. Give me a thumbs up if you're like, yeah, I've been there, done that, that's easy. Got it. Cosines and sines, I'm not going to be able to make a match. Not with weird, like, you can plug in cosine of 24.3. It's a nasty decimal. I don't know what to multiply by for elimination. Elimination. Doubling the whole thing, adding down. So what's the other way that you usually avoided because you didn't like it because it took more time, but now it's the only way forward? Substitution. What would substitution have you do in something like this? Solve for, you guys get to choose. You're allowed to. Solve for who? X or Y? Sure. You could have solved for X by adding, right? And dividing. And once you solve for X, what would you have to do? Okay. And once you plug in, it's all going to be in terms of Y, but that's the point. What am I going to be able to solve for? The Y to then plug in to solve for the X. But some of you are like, you want me to do what? But pause. Could you have done that mental jump like I did a second ago up there on the board? Are you to the point where you would know that it's 10 plus 2y divided by 3? Is that okay? If that's okay, don't be scared of this. Because we can do the exact same thing without having to go through our calculator. Now, just a few of you, and I did it with honors, and technically it did make things a little bit better for some of them, and that's fine if you want to do this. There are some people, when they're doing lab work, they just write down 1,012 different decimals. Just don't round it from the end unless you can say things. You could technically take this whole thing. You can totally just watch and see if you want to, and if it works for you, great, and if not, someone look at me. But if we were doing I'm not going to pull up the big calculator, it'll take too long. I could get the numbers for cosine 24.3 and cosine 44.5. As long as I'm in degree mode, which I am. And cosine of, and some of you would like this so much better because it will make so much more sense in your brain to go ahead and do something like 0.911403x and then plus 0.71325y equals 0. I can make numbers. If you like the numbers, we can make the numbers. We can plug this into our calculator and we can get whatever we need or whatever we want, right? So I can have the sign. I can go grab the other one, the sign. But some of you are like, I don't want to be writing decimals all day. Like, how annoying and tedious is that? Well, I don't want you writing decimals all day. I want you not afraid of the trig and able to work with him in a way that's efficient. But once again, no judgment if this is what you'd rather do. If this is what makes sense in your brain. Could you then, just like we did up there, solve for an x and plug into the other equation and then eventually solve for the y? Yes, they're just gross, but you can. Here's the or. Ready? Can you follow my logic? What did we solve for? X? Can you follow my logic and say x is equal to negative y cosine of 44.5 all over negative cosine of 24.3. Can you follow my logic? Just like I subtracted, or actually added the 2y divided the 3, I subtracted the cosine y, and I divided the cosine with a negative to get the x alone. Same math, just I didn't have to plug in. And now what am I going to do with that x, just like I would with the one on the board? Plug in. Don't be afraid of the trig. The longer you keep them around, the more you get to avoid these nasty decimals that otherwise you'd have to be rewriting. And this one would have been x equals negative 0.7132 blah blah y divided by negative 0.91 blah blah blah. And you could have done it in your calculator, and man, you're just number crunching all day long, and you'll get to a form of the answer, and it will be okay. Just man, you're gonna have to put a lot into here and be writing down a lot of decimals up here. This way, I'm like, hey, I have the same thing, and I haven't even gone to this yet. Now I go to plug it in, and when I go to plug it in, check it. Don't I now have negative y times cosine of 44.5 times, wait, a negative times a negative, that's just a positive, we'll forget that. And then question, what's sine of 24.3 over cosine of 24.3? Well, that makes life a little bit easier. And then I have my plus y sine of 44.5, and I have all of that equaling my 20,240. Don't I have a y in both terms? Can't I factor it out and just have my cosine of 44.5, tangent of 24.3, plus sine of 44.5 equal to my 20,240. At this point, kiddos, I'm going to my calculator for the very first time. I haven't introduced any error or any decimals whatsoever. I'm going to plug and chug the whole shebang and get straight to the answer of what y equals by just doing a nifty alpha y equals 20 divided by. Or now's a good time because I'm just going to be typing in all this annoying stuff. So, if I go ahead to degree mode, making sure I'm good to go, all you do is just throw in all those different trig expressions. So all those different trig expressions, I see cosine of 44.5 times my, now you could have done the tangent like me, or you could have written the sine of 24.3 over cosine of 24.3. That would have been fine. I'm just lazy and I'm like, I know that's tangent, no big deal. And I can go ahead and add whatever is left, which is that sine of 44.5.
Why is it only 20 then? And not
Oh, because I'm still in and I got distracted by more that she could leave to go to the restroom. 20,240. Yeah. Thanks, Vanessa. Throw it in and I got my one. What's the tension in the cable? 19,785. The crate's only 20,000. Man, that crate is holding like the entire thing. At least most of it. Look at all that weight. So I have that 19,000. Oops, it's the blue crane. I'll write it in blue. 19,785.832 pounds of force acting on the blue crane. But the cool thing is if you guys notice, with my substitution, I've primed and ready to go just to plug in that value that I have just chilling on my calculator into this expression, and I have x at the same time. Because substitution, once you find one, you go back and you plug it into the other one, and then you know him too. So then plugging him in right back here to the beginning expression that I started with. And go ahead and take that big old guy, and I forgot that I had him on this calculator. I can just multiply him by cosine of 44.
Wait, can you subtract it? Just subtract it and get rid.
You would think so, right? Let's see if it actually works out though, because I know it has to fit that one. So yours is more like a concept even as being like, well, he's holding most of it, so the red's just like barely there. Let's check it though. Divided by cosine of 24.3. Oops, not negative. The math says, dang, not a strict addition or subtraction as far as who's holding what of the 20,240. Which is a little bit crazy. 15,484.094. Not at all what probably most of us would have expected at the beginning if the crate was only 20,000 pounds-ish. And they're both working together. They both have a lot of strain. And the reason being is that they're both not lifting directly straight up. They're working at angles, and as they're working at angles, what was just a straight up force needs to be counteracted at 20,240. In a sense, in some ways, just got multiplied as far as the tension on both of those cables. But, I mean, imagine, what if the blue's capacity was 20,000? Well, then it's more than it can hold, so therefore someone else had to come in. And this other crane coming in, okay, it's below the 20,000 threshold. So it's within appropriate boundaries, even though, well, you still take it on a lot of force, but, or a lot of tension, I should say. But anyway, Vanessa was a good idea as far as like, hey, don't they just add up to be 20,000? But they don't. And that's why we need all these angles in here, is to show what's going on as they're working at diagonal directions, which is kind of crazy. Okay, this one. I know the concept. There were some tricky things like, hey, this guy's going to the left and up, or that guy's going to the right and up. I have to put signs in there to show the difference between the directions. I know the crate is pulling down, and so I had to offset it as far as the vector sum, the resultant. But it was still the idea of magnitude cosine angle, magnitude sine angle, the two vectors add together to be this overall. It was just this system of equations that could have messed a lot of you guys up, and you're like, I don't know how to solve it. Yeah, you do. It's just that math. It just looks worse. It just looks worse. But once again, you could have just gone and done tons of decimals, and if you had done the tons of decimals, your brain might have been able to process it a little bit better, because there's an x, there's a y. You could have solved for one, plugged in for the other. You just wouldn't have liked it, but no big deal. Have your calculator close. It's a tool for problems like these. But then the next one that we're going to do, the math is super easy. Hey, wait a minute. We just looked at an even in our homework. We just looked at an even, right? And it was super short. And it was like, what? Some of these are going to be super short. That one wasn't. This is one where the math is super short, but the concept is pretty complicated. The nice thing is, I'm going to give you all that you need. Because if the math is short, well, if we can just get the concept down, man, I can bust out the easy math, hopefully. And it all comes down to this little triangle right here. So let me show you. For any inclined plane, that's a snazzy way of talking about it, something on an incline. Any object on an incline. I'm going to generalize it, then we're going to use it over here. You have a few different forces that are acting on it. We're going to talk about, like, pretending that there's one wheel, one point of contact. We'll just talk about, instead of, like, there being force, or I should say weight distributed at different points, we'll say, like, one center of gravity right there. The triangle that ensues is going to be one that shows us straight down being gravity. That could be gravity. And that could be a combined of weight and gravity. That's going to be the straight down vector, which hopefully gravity, okay. But they might also say weight. And if they say weight, you have to realize, okay. Oh, hey. Combined weight of the boat and trailer. That's this guy. You also have one that's acting against the incline itself, perpendicular to the incline. So not just the gravity and the weight that's pulling straight down, but also technically like, hey, if there was a little mouse under this wheel, it would be squished because there is weight against the incline too going at this angle, not just straight down. So this one we would call the perpendicular force. Let's not try to fit in perpendicular to that tiny spot. Can I just use the shortcut notation of a right angle? We have that perpendicular force. And then we have this other little guy right down here that comes at a right angle to that perpendicular force. And both of these are technically talking about this incline. This one is parallel to the incline itself. because it's whatever is holding, whatever is pulling, whatever is having to keep this from sliding down. Because naturally, if it was just these two, of course it would be sliding down. But you have something holding it, whether it's brakes and it's just sitting there, but the brakes have a certain force acting on them, or whether it's like a trailer trying to pull it, whether it's a person trying to like drag it, whatever it is, there's something that's keeping it from sliding down. Especially if it's on a wheel. If it's an object, it could just be its weight that's keeping it from sliding down. So this one would be the force required to pull. Force to pull, the force to counteract. Different ways of saying it. I think in the book, technically, if they were doing letters, I think the letters that they would be talking about would be W for weight. That would be this guy right here. I think this one they would call force. And then even though this is another force, I mean, they all are. They're all vectors. They don't talk about this one as much in the examples that you see in your book, even though it is one that's very present. And here's the other crazy thing is that when they talk about an incline, they're talking about how inclined it is. If any of you guys have ever gone up to like Bakersfield, you have to go up the grade, or if you're going up like the, that'd be the Grapevine. There's a few different ones. Sorry, up by Santa Maria, there's a couple other ones too. So I get them all confused. But usually there's something saying like at what angle you're traveling, and the steeper the angle, the more like, especially for semi-trucks, their brakes have a tendency to have some issues. That's why you see the runaway ramps and whatnot, because of how hard they have to be braking because of the incline. Anyway, the incline, it's talking about the angle way over here, which seems totally unrelated to this triangle. And without going through all the geometry, you don't even need to understand it. You just need to know that angle ends up translating into this triangle right there. So this is the key. You have your weight working straight down. You have something keeping it from sliding. You have a weight that's perpendicular, and then you have the incline, which is over here in reality, but actually in the triangle. You can also think of, because of geometry, if we had done a lot of parallel line action, we could have eventually gotten it to be inside that triangle. I'll let you guys just jump straight here. Great picture for your card. Great picture for your card. If that's the picture, something on an incline. And how do we solve? And why was it so easy just a second ago? And we like, look at that. That's barely any work at all. It's because they use this triangle. It says a boat is on a ramp. Yeah, that's great. A force of 600 pounds is required to, well, who is it? Is it the gravity? Is it the pulling? Or is it the perpendicular? What's 600? Is it W? Is it F? Or is it the unknown guy they rarely ever use? Yeah, F. 600, the force required to pull, it's the one, see, literally the word pull. We have 15 degrees, we get to throw that in the triangle right here, just cuz, which is awesome. I like just cuz sometimes. And then find the combined weight. How do we do it? So-ka-toa. The concept was hard, but once you have the concept and you get the picture, math's easy. Solve for W. Sine is opposite over hypotenuse. You need W, just use sine. And then multiply W, divide them. But guys, depending on the problem, they can give you different information. Maybe they're asking you for the force perpendicular. They rarely do. Maybe they're asking you for, they give you the weight and you need to find the force. Maybe they give you the weight and the force, you need to find the incline. I don't know, but if you have the picture, it's okay. Just draw the picture and then do SOHCAHTOA, whatever you need. The final answer is going to be in pounds of force as well, because I'm looking at that unit that they use for the 600. That's word problem 1, that's word problem 2, word problem 3. Word problem 3. I need you guys to realize that for the test, you are not going to have to worry about doing angles with bearings. The problem is the book doesn't necessarily give you good problems without bearings, because in reality, physics wouldn't give you problems without bearings. I'm just trying to take away one of the difficult things along those lines. But even though the test isn't going to have bearings, that doesn't mean that you don't need to think about bearings at least a little bit and struggle through just a little bit. So here's what I want to show you in this problem, just kind of the basics of it. as you read through this word, I know we're getting close, but as we read through this word, I see wind and I see a jet. And I see also the wind has a velocity of 60 miles. That's its magnitude. And I see the jet as how fast it's trying to go. That's its magnitude. Just the idea I want you guys to be thinking about and seeing if it's easy or if it's hard. I'm not really telling you. We want to get components for both. And right away I can say, hey, magnitude cosine, magnitude sine, magnitude cosine, magnitude sine. What have I not filled in? The angle. Well, wait a minute. Hold on. The jet has an angle of 332. That would be this guy. I wonder if bearings are as easy as just throwing in the angle. In some ways, yes, and in some ways, no. The wind southwest, that's going to be a 45-degree angle. Go ahead and have a seat. Just take a second. The wind is going to be coming in. If they don't tell you an angle, you're just going to assume that it's like perfectly between south and west, which will be 45. That's a little weird. But what you overall want to do is just add the two together. When you see ground speed, I want you guys just to think of adding the wind and the jet. In theory, it looks pretty easy. The bearings make it a little bit trickier. I want you to think of the yellow, positive, and negative, and figuring out, ooh, what direction is it actually heading. All right, guys, get out of here. Try those word problems tonight. I'm going to spot check tomorrow.